So I'm not going to show a live demo today, but just this is a quick video I captured yesterday during one of the talks, or actually between talks, of North Pole running a YOLO network on all of us. And so if anyone's interested, I can set it up and you can see it running later. Okay, so I'm going to talk about North Pole. It's an inference accelerator from the brain-inspired computing group at IBM Almaden. This is the core team as of a few months ago. We've added a couple since then. And we're distributed across the US and even have a few members in Brazil and Japan. All right, so before I talk about North Pole, I'm going to talk about a little bit of history of our group in particular. So 20 years ago, our PI, Dharmendra Modi, started the group, and he realized, kind of as many of us have, that brains are really good computers. And if we could harness some of that power and efficiency, we could build better non-biological computing systems. And so he started, and the group started doing supercomputer simulations of large-scale spiking neural networks. They scaled up from mouse scale to rat scale, eventually to cat scale, a billion spiking neurons. And this, at some point, they applied for funding to DARPA for the Synapse grant and received that funding, which of course meant hardware. So in 2010, several of us from neuromorphic and neuromorphic adjacent labs, Kwabana's lab, Andreas's lab, Rajeev Manohar's lab, joined the team at IBM. And that began the True North era. So we started making some smaller chips, Golden Gate here, and then we made True North, and we published it in 2014 in Science, and it has 1 million spiking neurons, 256 million synapses, and it's a fully digital chip. And then after 2014, we spent the next several years building systems with that chip. So we built a single chip board, and then we put many of those together to build some other systems. And we even tiled chips on a single board to build one large sea of spiking neural networks. And then we kind of just were quiet for many years. We didn't publish anything. We didn't come to nice conferences or give any talks. We were just quiet. Everybody kind of thought we stopped doing neural computing. But in fact, in 2015, we were tasked within IBM to find what's the next inference accelerator and what should it look like? What should its architecture be? And so we spent the next couple of years looking at True North, other accelerators that were out there, and looking at where neural networks were going in general, where artificial intelligence was moving, and what did we need to build an inference accelerator for those new networks that were up and coming. And in 2018, we received funding from the Department of Defense and to build the chip. So we spent the next 3 years designing the logic, implementing the physical design, and we taped out the chip shortly before Christmas in 2021. In 2022, the wafers came back. We started packaging the modules and testing the chips. It's a very large chip, needs a lot of testing. And then we built our first fully assembled board last year, and we presented it at Hot Chips and published it in Science again. Okay, so now I'm going to go into what North Pole is. So the North Pole architecture is inspired by the brain and optimized for silicon. And what I mean by that is there are a lot of features in the brain that make it very efficient. Now, I don't know how the brain works, but I can see those features, and I know what we can take and put into machine learning acceleration on chip. So in particular, we did not take spiking in this one, unlike True North. Okay, so first, the high level view. This is contrastive architecture slide. So North Pole is on the right, memory is in blue, and compute is in red. And you can see North Pole is kind of purplish. So especially if you squint or you need glasses like me, it looks relatively purple. Compute and memory are intertwined throughout the chip. And of course, you see the same thing in the brain. There is no memory separated from compute. Whereas if you look at the kind of the typical architectures of today, GPUs, TPUs, CPUs, you see compute in these bright red blocks, and you see these big blue blocks that are generally caches. And those connect to off-chip DRAM. And all the data moves from DRAM to cache to compute cores and often back and then back to DRAM. Whereas North Pole, everything is on chip. We have no DRAM. and we have no centralized memory. Okay, so now you saw it's a multi-core architecture. So let's zoom into a core, in particular, the core compute. So compute is again in red. The main engine of compute is the vector matrix multiplication unit. It can do multiple precisions, but all of them are relatively low. Again, like the brain, neural networks, we know our brains don't need particularly high precision for synapses, but some synapses are higher than others, so we're flexible. So we do 8-bit, 4-bit, and 2-bit precisions. And depending on which precision you choose, every VMM can do 2,000, 4,000, or 8,000 operations every cycle. So we're trying to copy the parallelism as well. And then we tile these cores and we get really massive parallelism in one chip. And as I said, it's mixed precision and it's not fixed. You don't take a core, set it to 2 bits, and then it's 2 bits forever. Instead, depending on the layer and that layer's precision needs, we can change as we go through the deep neural network. The VMM's output goes to the vector compute unit, which does operations such as accumulation, gating, and other element-wise vector operations. And the output of the vector compute unit goes to the activation function unit, which does our nonlinearities. So sigmoids, rectification, any other nonlinearities you want for the output of your neural network. And this is all fully pipelined. Okay, so now memory. Memory sits right on top of compute. Even the compute units have their own memories. So the VMM has a weight buffer right on top of it that delivers weights as needed. The vector compute unit has a partial sum memory, which is like a scratch pad. So any kind of memory it needs, anything it needs to store temporarily, it can do that there. And then below both of them is what we call a unified memory, which can store weights, program, and activations. So a typical layer in a neural network, the activations are sitting in the unified memory. They go to the VMM. The VMM's output goes to the vector unit and the activation function unit. And then that output writes back to the unified memory and is generally the input for the next layer in the deep neural network. So the data movement is extremely local. We try not to move data any more than we have to. And then next to these is the control. It's a fully custom control. It's not any existing ISA, and it's not VLIW. Instead, every core has 8 threads that control the different units, and it's completely deterministic and pre-scheduled by the compiler. And that means we don't have any kind of branching. So nothing is data dependent. If you get halfway through your network and some feature is 0, you don't stop computing. You just compute the whole network. Which makes sense for neural network accelerations. We generally don't have conditions like that. We don't have a cache, so we have no cache misses. We don't have stalls because everything is pre-scheduled. So whenever a unit is handing off data to its neighbor, that neighbor is expecting it. We don't have anything like speculative execution or any additional complexities like that. Okay, so the layout looks a lot like the block diagram. The VMM in the upper right, in red is the compute, and in blue is the weight buffer interspersed within the compute. The vector unit is next to it. The red is the compute, and the blue is the partial sum buffer interspersed with it. And then below both of them is the larger unified memory, and then the control is mostly off to the left. Okay, so now we have one tiny neural network accelerator, but we want a lot of them, and we want a bigger one. And so we need these cores to work together, and so we need a lot of communication. And for communication, we have 4 networks on chip. 2 of them are loosely bio-inspired. The activation network on chip, which handles longer range connections between cores. The partial sum network on chip, which handles connections to the nearest neighbors. So if a core wants to talk north, south, east, or west quickly, it uses the partial sum network. And this one is really important for the cores working together as a compute engine. If one core is doing, if the cores are doing a convolution, and this core computes something that the neighbor needs, it just hands it off to the neighbor through this partial sum network, rather than redundant communication or any other mechanism. And then the other 2 networks on chip, which are not bio-inspired, are the model network on chip. This one is important for things like convolutional networks because it can deliver weights during layer execution. So in core-based networks like true north, the weights were fixed at configuration time. And so if you needed many cores to use the same set of weights, those had to be replicated across cores, which is not an efficient use of memory. So here we allow broadcasts to all cores or subsets of cores if they use the same memory. And then we have the instruction network on chip. And this is just what it sounds like. It delivers instructions to cores for the next layer. So in layer 1, we deliver the instructions and queue them up for layer 2. Okay, so this is what the network on chip wiring looks like. More than 4,000 wires in the X direction and the Y direction. But we can take those cores and tile them. And we like to think this is brain inspired, but it's really just very convenient. So in Cortex, you have hypercolumns. And if you look a little bit over in V1, for example, you have a hypercolumn that looks similar. We have a core. We take that core and we tile it into a sheet of cores to make our chip. And really, this is, from an engineering perspective, we build one core and we tile it is a lot more efficient than trying to just design a whole massive chip. So we take those cores, we implemented this design in 12 nanometer FinFET process. We have 16 by 16 array or 256 cores. Spread across them is 192 megabytes in the unified memory. And then on top of the core array sits a frame buffer. And this is just a memory where while we're processing one image or one batch of images, the next one can be loaded into the frame buffer. Okay, and the whole chip is just under 800 square millimeters with 22 billion transistors. And it's fully functional in first silicon. Okay, so one unique thing about North Pole is that it supports spatial computing. And this term is used a lot in different contexts. So really what I mean is we can preserve topography as we compute. And I'll show you what that means in a second. So this is an image of a juvenile bald eagle. And this image is important to us because this is the image we used for our month-long gate-level simulation verification before we taped out the chip. And we ran a small ResNet, a ResNet 18. And the way we ran it was end-to-end. We simulated the whole thing. And so we take the bird image, we load it into the frame buffer by chopping it into 16 columns. Then the frame buffer loads it into the core array by chopping each column into 16 rows, and they just propagate down to each target core. So now each core has what we call a tensorlet, a little piece of the whole tensor. And then it can operate on them. All the cores, it's convolution, so all the cores can do the same thing on their tensorlet for the first several layers. And so this is the first layer, and what we're showing here is just our estimate of the power of the VMM in that first layer. And it's not surprising. You see that where there are more features and more contrast, you get more energy consumption. And then we keep this topography through the layer. So this is an image from about halfway through the 18 layers, so around layer 9. So there have been many convolutions and many pooling layers. So the image size is not the same anymore, but we preserve that topography in each core. So you can see when we average all the features, you get something that still looks like, roughly that same bird, at least that same bird shape. And this is very different from, how most accelerators work, how a GPU works. The GPU, you still take a piece of the tensor, you farm it out to a core, and then you bring it back to the cache. But there's no sense of space. Cores don't communicate with each other. There's no sense of locality. And by doing this, we save a lot of energy. We're not moving data around for no reason. We only move it around when we really need to. Okay, so who cares? Why should we even build accelerators? And the reason is because AI is really, really expensive. Right now, the data center power usage is growing extremely rapidly. It's, I don't know, something like single digit or maybe even close to double digit percentage of total electrical power consumption. So that's a lot of energy, and buying GPUs is very expensive, and so powering these data centers with GPUs costs a lot. So our perspective, kind of our baseline fundamental premise in our group is that GPUs probably aren't the best choice for inference. There are a lot of tricks we can play and a lot of things we can simplify to make better hardware for inference, or more efficient hardware for inference. Okay, so how are we more efficient? So here are our fundamental metrics. On the x-axis is our energy efficiency, frames per joule or frames per second per watt. On the y-axis is our space efficiency, or really our transistor utilization efficiency. So frames per second per billion transistors. If we give you a billion transistors, how many frames can you do? And we're showing this for ResNet 50. And it's not that ResNet 50 is the best network. It's just the one that everybody gives their data on. So that's why we choose it as a point of comparison. Okay, so here are some CPUs in blue. These are from Intel. Here are some GPUs in green, mostly from NVIDIA, one from Intel, and some accelerators from startups. And then if we put all these there, you can kind of see what the landscape looks like. So right now, the Jetson board over here is the most efficient, and the NVIDIA H100 is the most transistor efficient because it runs really fast, so it uses its transistors well. Now, I'm gonna keep the same data, but I'm gonna scale the axes. Okay, so still H100 at the top, Jetson over there, and now I'm gonna add North Pole. So North Pole is way, way over here. We're really efficient. We do a lot more frames per joule, and we use our transistors a lot better. We do almost 2,000 frames per second per billion transistors. And the best comparison from my perspective is comparing us to V100. This is a GPU in a 12 nanometer process, which is a similar process to what we used. And we're about 25 times more energy efficient and about 5 times more space efficient. And our throughput is about 5 times higher, and our latency is lower. And so you can see even the H100 is 4 nanometers, which is several process generations beyond our 12 nanometer. So if we migrated to 4, we would be even further out in both the energy efficiency and transistor efficiency. And this holds up for other networks. So this is YOLO v4. There are not as many dots because not everybody publishes on YOLO v4. And then also for BERT base, this is your entry level language model. It's not a large language model yet, but it's entry level. And we still do very well in this. And it is a transformer. So we can do transformers. Okay. So now, while I still have a couple minutes, I'm going to talk about mixed precision. So how do we use the 8 bits, 4 bits, and 2 bits? So we have 2 algorithms that we use for training, FAQ and LSQ. And LSQ pretty consistently, and its derivatives, are near the top of the accuracy that you can achieve with lower precision weights. So those are shown here. But what I really want to talk about are Eagle and ALPS. So I had nothing to do with these algorithms, but they're really cool. My colleagues designed them. So these tell you what precision you should give to LSQ. So should you use 8 bits? So it's kind of the standard way everyone compares is they make the first and the last layers of the network as high precision as they can. So you want to bring in your data with the highest fidelity you can, and you want to make your final decision with the highest fidelity. So those you generally just fix at very high precision. And then if they're comparing 2 bits, you just make everything 2 bits in between. If you're comparing 4 bits, you make everything 4 bits in between. But that's not going to be the most efficient because some layers are a lot more tolerant than others. And that's why we developed these 2 algorithms down here, Eagle and ALPS. So Eagle is a very fast running algorithm. If you don't have time to do brute force, you use Eagle. And what it looks at is the entropy of the weights of a pre-trained network. So you train with full precision. You look at the weights in every layer, and the weights with very high entropy, or proxy for entropy, those you use higher precision, and the ones with very low entropy you use lower precision. And this one runs in CPU seconds and minutes. And then ALPS is a little more thorough. So it does a little better job than Eagle in some networks. And what it does is it does a real sensitivity analysis. So you take your fully trained network with high precision, and one layer at a time, you put in low precision and see, does that affect the overall score? And the layers that are particularly sensitive, you use higher precision for those, and the ones that are less sensitive, use lower precision. And these 2 algorithms are also among the best in getting the most accuracy for the least cost in terms of 2-bit and 4-bit operations. Okay, I have one slide on the software toolchain, which is a crime because so much effort goes into the software toolchain, and it's so important. the best hardware without a software tool chain is a paperweight. It's just not useful. If you can't let people use your hardware, it's not going to go anywhere. So I built lots of chips that only I could use, and it was fun. But this is a lot better, making it available for others to use and making it, easy to use, or at least as easy as possible. We learned a lot of that with True North. Some people in the audience used True North out of its kind of intended space, and they learned the hard way that, if it doesn't have a really good tool chain, it's really challenging to make hardware do what you want it to do. Okay, so this is what our software development kit looks like. It's containerized, so you can run it in Podman or Docker. And it has two flows, a train flow and a run flow. When you're training, it's pretty straightforward. It's pretty conventional. You run PyTorch pretty much just like you normally would. You just swap out the standard PyTorch layers for the lower precision North Pole PyTorch layers. And then you run just as usual. And when you're done running, you get an output network that you hand to the North Pole compiler, and then the compiler does all the work for you. So no more hand mapping, this neuron goes here, these weights go here. The compiler does all of this. It distributes where all the weights are going to live on the chip, where all the instructions are going to live, as well as all the sequencing. And in fact, the host computer doesn't even really have to do anything. All the host does is put a tensor in, put an image in, tell it to go, and then when it's done, pull the result out. It doesn't have to micromanage all the different layers as you often see with accelerators. And that's what the North Pole runtime API does, is just that put and get operation. So whatever application, a C++ application or Python application or whatever, running the chip just uses that. If you don't have hardware available, there is the North Pole validator, which is a cycle accurate and bit accurate emulator, but always have the hardware because it's way faster. Okay, so we've got 2 minutes to go through North Pole systems. So this is our board that we use, and it has the North Pole chip, an FPGA, which is just a PCIe bridge. And then this is the fully assembled card. So there's the card, heat sink, covers, and tailstock. So this can go in a server, just like this server. So the video I showed at the very beginning was actually run on a server just like this. This is the North Pole card on the right. We have a number of these sitting in a data center, well, not data center, a lab in San Jose. And then we can add more cards to other servers. So this one has 4, it's still a 1U, so it's pretty slim. Actually, I'm gonna go back 1 second. So this one I brought this one to ISSCC a couple months ago. I wanted to bring it here, but even though it's called an edge server, some of you will take issue with that, but it's called an edge server and it's relatively small, but it's really loud, even when you turn the fans all the way down. And I just couldn't do it in this auditorium. All right, so I'm not going to show a live demo, but the last thing I'll show is just a video. So this was taken in San Jose, near our lab. One of my colleagues just took out his phone and took some video. And so this was just run through North Pole, the YOLO v4 off-the-shelf network. So we just downloaded it from, I think, the PyTorch Zoo, replaced all the middle layers with 4 bits. We didn't even optimize, and trained it back to state-of-the-art accuracy. And then it runs really well. And in fact, on YOLO v4, we can do 1,200 images per second. So if you're doing, that 40 cameras at 640 by 640, at 30 frames a second, one chip can handle all of that. Okay.